It was working earlier. It was working earlier. Can I go to the presentation? Like that. Okay. Yes. Yes. Okay. Perfect. We can start. So let's start with what is clustering. If clustering is an unsupervised learning technique that aims to partition observation into groups that we call clusters, such that points within the same cluster are similar, and we'll see what does it mean similar, and points in different clusters are dissimilar. Similarity can be defined by a distance. By distance measures, usually, and in the example that we will see, it's the Euclidean measure. We can divide in two broad categories, hard clustering and soft clustering. Hard clustering means that each observation is assigned to exactly one cluster. You can see in the left diagram, each point belongs to just one circle. While soft clustering means that each observation is associated with a probability distribution. So we can say that a point belongs with a 70% probability to one cluster and with a 30% probability to another. As you can see in the second diagram, there are different techniques for each one. We will see k-means for the hard clustering and GMNs via EM for the soft clustering later in the lecture. So, if this thing goes, as we said, k-means is a hard clustering algorithm, which means that each point belongs just to one cluster, and each cluster is represented by a cluster centroid, which is a point in the feature space. Usually is the mean of the points assigned to them, to that clustering, which is the goal of k-means. It's to minimize what we call cluster error, which is the Euclidean distance between the data points and their nearest cluster centroids. How can we do that? So we can proceed in step. The first one is the initialization. So we choose k initial cluster before starting with our data set. Often it's selected randomly from the data, even if this initialization isn't the best one, because initialization affects the convergence. We are sure that the algorithm converges, but only to a local minima. Usually doesn't converge to a global minima if we start with a bad initialization. There are algorithms like k-means++ that can do that, or you can just do the algorithm for more iteration and see when it converges better. So after the initialization, we have the assignments. So each point are assigned to the nearest cluster centroid, so measuring the Euclidean distance, and this should minimize the objective for a fixed cluster centroids, as you can see in the image. Third, we have the update. So each cluster centroid is updated as the means of the assigned point for each cluster. This decreases the objective for the fixed assignments, and then we can repeat the step until convergence. So overall, the objective is to minimize for all the clusters this local k-means loss. So the minimum for each point of their nearest clustered instance. So we initialize the cluster centroids, we assign them using this arg minimization local loss. We update the centroids and we repeat until the convergence. So now we can go to the federated k-means, but before that, you can see the term cluster associated with federated in two ways: federated clustering and cluster federated learning. Which is the difference? Federated clustering, we want to cluster the data points that belongs to the different devices. While for cluster federated learning, we want to cluster the device, so maybe they have the similar data distribution in their data set, and so we want to teach better models for each cluster of devices. We all obviously are looking at the first one of this image. So what is the motivation for federated learning? We have a number of devices. Each one has a local data set called DI, and the goal is obtaining a global clustering of the total data set as we could access to the global dataset, but under the privacy communication constraints. So each dataset device cannot really communicate the raw data of their dataset to their neighbors. And obviously, if we will do the clustering to the singular devices, having a limited amount of data will result in a poor result than compared to having all the data, the global dataset accessible. So formally, we have n devices that are indexed by I. Every device has a local dataset, di. We have a communication over a graph using neighbor links. And each node maintains what we call local cluster centroids, which is an array of their centroids. The objective is learn the cluster centroids without exchanging raw data. We will exchange just the centroids between the devices. One problem that arises that one could argue that we can just average over the centroids between the devices, but what happens that in k-means the cluster labels are arbitrary. We can call each centroids as we want all over the devices. So, for example, looking at this poor image, we can see that directly averaging cluster centroids that are colored similarly, which will result in mixed unrelated cluster. What we want to do in reality is to mix the first one with the first one, so following the green link, and the second one with the second one. How we can do that? Having a permutation invariant way to measure the disagreement that we said before. So how can we do that using generalized total variation minimization? We have our objective function, which is the sum of all the nodes of a local k-means loss, like the single case k-means, and the graph total variation, which is the sum all over the links of the discrepancy. This term encourages neighbor agreement, so as big as the lambda, as big we want to force the agreement between nodes. How we define this discrepancy? So we need a disagreement that is symmetric, otherwise we could have the same problem as before. So this is measured between set of clusters, and we have two terms. The first one is what we call the match for the I node cluster to the nearest centroids in I prime, and the second one, which is the symmetric term, which match each I prime cluster centroid to the nearest in I. As we will see, usually it cannot be symmetric every time. For example, this is a symmetric scenario. Every cluster centroid in node I has its counterpart in node I prime. And obviously, it's the same for the reverse. Each node in I prime is connected bidirectionally to the cluster centroids in I. But what happens in a situation like that, this asymmetric scenario, in which, for example, W2 and W3 are very close to each other, so their closest one in node I prime is still W2 I prime. In this case, if we had just this first term in the discrepancy, we will have a low score and we will be content with the result. But if we consider also the reverse, we will see that W2 I prime will be close to W2I, and W3 I prime will be close to W3I. So that means that overall we have a much higher score and much higher disagreement between the agent. So we want to assess this problem. So how we can solve GTMin? We use this blockwise optimization. We iterative block each neighbor's cluster centroids at iteration t. So every neighbor updates its own block using the neighbor's block from the previous iterate as they were fixed. And this update can be executed in parallel. What we need is just the dataset of the node that we are considering and the cluster centroids from the neighbors. We don't need a central server or whatsoever. We have our k-means loss local and the neighbor coupling, in which again we just need the cluster centroids from the neighbors. This can be non-trivial. So there is a practical approximation that we can apply in this case, which is apply standard k-means on the augmented local dataset. What does it mean? That we still have our objective function, so the local k-means, but instead of having the GTV midterms, we just receive from the neighbor the cluster central of them, and then we add them to our dataset as they were just new points. And at the third, we run k-means of this augmented dataset, and then we broadcast these updated cluster centroids to the other. That can be a way to solve also this problem. Any question? I don't think so.
Hello, so I'm gonna take over from here if there are no questions. Any questions? No, okay. So now we're moving from hard clustering to soft clustering methods with Gaussian mixture models. I assume that you already heard about the Gaussian mixture models, but we're gonna still cover some basics just to make sure that we understand all of the basics and terminology. So imagine that you have collected some data, and let's say it's a 1D data as represented on this very simple sketch, and this curve is a density curve. So by looking at this curve, you can see that there are 3 peaks, and we can assume that this is a mixture of distributions. It's a multimodal distribution. And one of the maybe simplest idea is to try to approximate this distribution by a mixture of other distributions, and we can choose, for example, simple Gaussians. And we can specifically assume that these data points, this data is generated by a mixture of 3 Gaussians, because we have 3 peaks or 3 modes. And we also can assume that each Gaussian is representing one cluster. So we have 3 Gaussians or 3 components or 3 clusters. So we can introduce the variable z, and this variable z will indicate from which cluster the data point was generated. Basically, it's a binary vector z, and each element can be either 0 or 1, and the sum of all elements must be equal to 1. So for our 3-mode distribution, the possible values for this latent vector is 1, 0, 0, 0, meaning that this data point was generated from the cluster 1 or the Gaussian 1. Another possible value for this latent vector is 0, 1, 0 and 0, 0, 1, depending from which cluster the data point was generated from. It's called latent or hidden variable because we don't know from which cluster, from which Gaussian distribution the data point was generated. Thus, it's called hidden or latent. Now, if we would know from which cluster this data point was sampled, then computing the probability for each data point is relatively easy. So given that we know from each cluster, is it from the blue Gaussian, red Gaussian, or the green Gaussian, the data point was sampled, then we can just use the formulation for the probability of a normal distribution. But here we also have to assume that we know the parameters for each Gaussian, because each Gaussian is characterized by mean vector covariant matrix, which means that our each cluster is associated with the mean vector and covariant matrix. So here we have a few more components to build our GMM model, or probabilistic or generative model. We are going to introduce mixture weights and denote it pi c, So this is a probability of sampling the data point from cluster 1, 2, or 3. So for each cluster, there is a certain probability associated with it. Now, the second formulation is the same as this one, just because our latent vector z is a binary vector. So if you, and it contains only 0 or 1s. So if you put this pi c in a power of 0, then all of the value is going to be 1 except the one where c is equal to 1. So these are the same formulations. Now, this probabilities value, of course, should be between 0 and 1, and they should sum up to 1 as a total probability. Again, here we have the same conditional probability for our data point x, given that we know from which cluster it was generated. And again, this is the same formulation, but just slightly in a different form, using the fact that this latent vector is binary vector. Now, what we have here is two probabilities, p of z for the latent variable and conditional px given z. So in reality, we don't know anything about the latent variable, right? So what we can do is we can marginalize over this latent variable, meaning that we are going to sum up over all possible values of z. Our random variable z is a discrete random variable. It's a binary vector. So what we can do, we can compute this pz with the conditional probability, which gives us the joint probability of a data point and the latent variable. And that results in a marginal distribution for the data point. Now, that's how we arrive finally to formulation for the Gaussian mixture model. As you can see, we arrive at this formulation by substituting pz and the conditional probability from what we already discussed. And we can see here that this is a basically weighted sum of Gaussian probabilities. So this is why it's called Gaussian mixture model. And then each component or each cluster contributes proportionally to the probability or mixing weights pi c. So this is just the basic of the Gaussian mixture models. And now we talked about that in this case, instead of hard cluster labels, we assign to each data point soft labels, meaning that each data point can belong to each cluster with a certain probability. So how do we compute these soft labels or soft assignments? So here we denote these soft labels as gamma. And basically, it's a posterior probability for the latent variable zeta, given our data point. And essentially, it's for each cluster, we have just a Gaussian distribution weighted by corresponding mixture weights and then normalized by the same quantity for all the clusters. So this gives us probabilities that data point comes from each of the clusters. Now, just to recap and illustrate what we covered so far. So we have marginal data probability where we ignore all the cluster assignments or labels. So essentially we have our density, which is a mixture of distributions. We have our data points, but we don't know to which cluster or to which Gaussian this data point belongs to. Ideally, what we want to discover is complete data where we know the data, where we have access to the data points, but also we know the cluster assignments. So in this case, these colors correspond to where each data point is sampled from. These data points, the blue data points, are sampled from this blue Gaussian, and the same for other ones. Now, the third picture is illustrating how we compute the soft assignments or responsibilities. So here, the colors for each data point are blended proportionally to the probabilities, the data point belonging to each cluster. So for example, here we can see this green point. Do you see my arrow? Yeah, so green point. So this data point comes from the third green cluster. But if we compute the soft assignment, we can see here that it's red, because it's pretty obvious that there is a very high probability that this data point can be sampled from the second cluster. And this is reflected in these soft assignments. Also note that how this color gradually changes from blue to red to green, meaning that the boundaries between the cluster, they are kind of blurred. That's why you have this kind of soft assignments, and the data point can belong to different cluster with the different probabilities. So here we're just going to recap our formulation and introduce a couple of more notation simplifications that are useful for later discussion. So what we have here, we have pi, which are mixture weight. So each cluster have a corresponding probability. Then each Gaussian, each cluster is characterized by mean vector and covariance matrix. We're gonna collect all of these parameters for each cluster or each Gaussian in a variable WC. C corresponds to just a cluster index. And then for all clusters, we're going to stack all these parameters and denote it as W, just for simplicity, so we don't have to write out all of these parameters all the time. Okay, so now we covered what is this probabilistic Gaussian model, that it has like a certain parameters. Then we have this soft labels. And next question is, okay, how we actually find these parameters for these Gaussians? What actually we are optimizing for, how we can find these clusters? So, and for Gaussian mixture model, what we want to actually find are parameters W, meaning all of these mixture weights, mean vectors, covariant matrices for each cluster that would maximize log probability of the data set, or equivalently, that would be sum of log probability for each data point. Now, optimizing this directly or maximizing this log likelihood would be tricky, because first of all, we don't know the cluster assignments. We don't know anything about this latent variable. Then we don't know anything about the parameters for each clusters, for each Gaussian, the mean vector and the covariance, right? And also we have this log sum, which is also a little bit tricky to handle. So what's usually people do in practice, they use expectation maximization algorithm. It's iterative algorithm where we kind of split this optimization in two steps. So first we start with some initialize some, let's say, random parameters for each cluster, for each Gaussian. Let's say we choose some mean vector and covariance and mixing weights. And then given these parameters, we compute these soft labels responsibility. This is so-called E step. And then on the next step, we update parameters given these responsibilities that we computed in the first step. So from where these formulas are derived. So essentially, if we go back to this log likelihood, so if you compute gradient of the log probability with respect to each of these parameters, and then set this gradient to 0, you can derive these closed form analytical solutions for each parameter. So that's how you can you can actually check it with the pen and paper that these formulas are correct. And a little bit of illustration how this algorithm works. So let's say we have, in this case, 2D data set, these green dots, and then we initialize two Gaussians. In this case, we have these red Gaussians and blue Gaussians, which both they are spherical. This is first initialization step. Then we compute responsibilities or soft labels. So here you can see that now each data point belongs to, have a higher probability belonging to either blue cluster or red cluster. Now, after computing these probabilities in the E step, we're moving to the M step where we update the parameters. And you can see here that the shape of our Gaussian is changed, meaning that obviously the covariant matrix is changed now. It's anisotropic blob, anisotropic Gaussian. And then we just repeat these two steps many, many times until convergence. And the end result here, as you can see, two Gaussians or two clusters, and the colors for each data point with the a dominating probability to which cluster they belong to. So this is a very classic way of doing the soft clustering with Gaussian mixture models. The problem is that this algorithm is not suitable for all cases. First of all, we assume that we use all data set, like a full data set on each iteration. So if you have very large data set, then that might be a problem because you need to do some kind of distributed optimization. Now the M step requires analytic solution, the closed form update. So if you want to modify your M step, then that's going to be a problem. And again, yes, it's not suitable for large scale data set, for federated, distributed, and settings, and it doesn't work if you don't have this closed form solution. So simple extension of this algorithm would be just introduce gradient EM, where we replace this closed form M step with the gradient ascent. So in this case, we can optimize function, which is like our log likelihood, but we also can add some additional, like a penalty or regularization term. So with this gradient EM, then we can implement distributed learning on mini batches of the data set, so we can store the data sets on a different machines. We can also implement different federated algorithms where this penalty term can be some sort of constraints for the loss function. Yeah, so basically that's the implementing, introducing the priors and penalties via this regularization term. Okay, so we covered the basics of GMM, EM, and gradient EM. Do you have any questions at this point? No questions. Okay. All right, so now we have this regularized log likelihood optimization problem. So how we move from this to federated learning with GTV mean optimization? Because in this course, the main focus is this GTV mean formulation. Well, to formulate it as GTV mean optimization problem, we have to appropriately choose this regularization term. So you saw in the previous lectures that these regularization terms usually is some kind of distance matrix or penalty which penalizes the difference or discrepancy between the models on a connected nodes, right? It could be dependent on parameters, and it could be, for example, squared Euclidean distance or something else. So by introducing appropriate regularization term, we can force consistency of the connected models on the connected nodes. And also our goal, again, we are not sharing the raw data, we only sharing the neighbor parameters. So basically, the main summary of this is that by choosing this regularization term appropriately, we can reduce this regularized log likelihood to the instance of the GTV optimization. Now, the Gaussian-Mikshi model is a probabilistic model. So, and because of that, we have opportunity to use something else, not just Euclidean distance. So before we use this penalty between the parameters of the model based on this Euclidean distance, but because we are working with the distributions on each node, now we actually can try something more interesting. For example, we can use the Kalbeck-Leibler divergence as a matrix how different models are on a different nodes. So this KL divergence is a very common standard way to measure the difference or discrepancy between different probability distributions, between two probability distributions, to be more precise. So to measure the KL divergence between the first probability, P, and the second probability, Q, what we need to compute is expected value for the random variable, which is log of probability of sampling data point X from the distribution 1, which is P, divided by probability of sampling the data point X from the second distribution, which is distribution Q. And this data point X is sampled from the first distributions, P. So couple of properties of these metrics. So it's positive, it's equals to 0 only if the distribution is same, if the distribution P equals to distribution Q, and it's not symmetric. So if you change the order of the probability, it's not the same, so it's not symmetric. And in the case if we cannot compute this expectation of log of the ratio of probabilities, what we can do we just can substitute it with Monte Carlo sampling, meaning that we just compute some average of this log of ratio of probabilities. Okay, so as I just said, it's not symmetric. The KL divergence is not symmetric. So, and normally when we are talking about the distance metrics, we want to this distance matrix to be symmetric. So whether it's a distance from node I to node I prime or from node I prime to node I, it should be the same. That's our goal for the metrics. So in order to make it symmetric, we introduce this symmetrized KL divergence. And so basically it's just the sum of the KL terms from one node to another and the opposite direction. So here we can see that this is a divergence of a node, of a probability distribution on a node I relative to probability distribution on a node I prime, and in the reverse order on a node I prime relative to I. So in this case, now our distance matrix is symmetric. So it doesn't matter from which node, in which direction we computed. And now if we use this divergence matrix, which reflects how similar the probability distributions on each node are, we can use it as a regularizer, and we can penalize the models on the nodes in a such way that we enforce the similarity between the connected nodes. So this is our final formulation. Again, we have some graph G with the number of nodes and the edges, and these edges are undirected. And each node has a local data set DI and local GMM model with the parameters WI. So what we want to minimize over all graph, We first want to minimize local loss function. In our case, what we actually want to do is maximize log likelihood on the local data set. But additionally, we introduce this penalty term, which enforces all of the connected models to to result in a similar GMM models, in a similar distributions. And again, because solving these problems simultaneously, it's a little bit tricky. So what we're gonna do, we're gonna use the block-wise optimization for each node. For example, for node I, we assume that all of the other parameters are fixed. And then we only optimizing with respect to the parameters on the local node. So we're minimizing the minus log likelihood or negative log likelihood plus our penalty term. Now, if we write out, as you remember, this symmetric KL divergence term is just a sum of two KL divergence term. If we write out, and just to remind, so we have here expectations, we have log here, and you can, because it's a log of division, we can rewrite it as a log px minus log qx, and etc., etc. So we can simplify this symmetric KL divergence term, and then we can drop all of the terms which are not dependent on local parameters wi. So if we do that, if we simplify all our terms, we end up with this so-called surrogate loss function consisting of three terms. The first one is just minimizing minus log probability for the local data, which is equivalent to maximizing the log probability for the local data. So the second terms is the neighbor cross entropy. So here we are minimizing minus log probability, but in this case, the data points are coming from the distributions of neighbors. So we're able to do that because in our setting, each node sharing each parameter with the other nodes. So given the parameters of neighbors, we can actually sample from this mixture of Gaussians some number of sample and then minimize this minus log probability. And then we have third term, which is a little bit counterintuitive because here we are minimizing log probability. So you can see the sign is different here, but intuitively, and here we are sampling data points from the distribution on a node I at the iteration t. So intuitively, that would prevent overfitting the distributions to the distribution on a node I on a previous iteration. Okay, let's go through the summary of the algorithm. So what we need to do for the update on the node I, we need to generate self-samples, meaning that we need to draw samples from the mixture of Gaussians, which I learned on iteration t on a node I. Then we also need to sample data points from neighboring distributions. So for each neighbor, we have parameters for this mixture of Gaussians, and we're going to sample the data points from there. Then we construct this surrogate loss, and then we can just use any kind of gradient-based optimization methods, for example, autograd in the PyTorch, and update the loss function with respect to parameters on the node I, wi. And that's going to be our parameters on iteration t+1. So any questions at this point, because it might be a little bit confusing? No questions, okay. Okay, so now, as we saw here, we have these three terms, and we have to use some gradient-based optimization, which might be a little bit time-consuming or maybe requiring a little bit of more computational resources. But what we can do, we can actually simplify this problem. As you can see here, we have these two negative log likelihood. So these, in the first terms, those data points from the local data set, and these data points from the neighboring distributions. So if we drop this third term, this self-likelihood, we have these negative log likelihood that we need to optimize for, and we can implement it in a very simple way. We can take these local data points and these data points generated from the neighboring distributions, stack them together, and create augmented data set. And then we can use any kind of high-level library, for example, scikit-learn, and then just use for example, in scikit-learn, there is a GMM function, and just fit this augmented data set to find the solution. So this is much simpler than implemented with the gradient descent. And it's, in many cases, is as good as optimizing this full surrogate loss. And in fact, this is one of the, a part of your assignment for this lecture. In this assignment, you will have to train the GMM models in a federated manner by constructing this augmented data set. And yeah, so basically, the only thing that we do here, we just drop one of the terms in this surrogate function. Okay, so in this, just summarize what we covered here. Today we covered hard clustering, soft clustering methods. Again, we are concentrated on GTV mean optimization approach, where GTV mean term can be constructed for k-means using the Euclidean distance between the centroids of local centroids and the neighboring centroids. Or in the case of probabilistic models like GMM, we can use, for example, KL divergence and construct this GTV term using this kind of divergence metrics. And again, in practice, we use blockwise optimization, where we are just optimizing with respect to local parameters, and all of the other parameters are treated as fixed. And again, we also can come up with some simplified approximation of solutions that are easier to implement, and in many cases, that's just enough. In many cases, you don't need to resort to these full loss functions to find the good solutions. All right, any questions? No, no questions? Okay, so we have a little bit of time. If you will come up some questions, you can ask them. Okay, I see some questions. Okay, there's a question about soft assignments, and okay. Can we use, okay, I'll start with the last one. Can we use different divergent computation methods? Well, in principle, yes. Why not? I think from what I understood, checking the literature for federated Gaussians, it's not, there are not that many papers about this regularized log likelihood optimization. So I cannot say that there are like established methods or established these GTV mean terms to optimize for GMM. But in principle, I think, yes, why not? But you will have to try it experimentally, whether this different divergence metric works, and then also maybe prove it theoretically that it actually makes sense. So it's still underdeveloped area, I would say. Okay, so we are gonna go back to soft labels, and I'm gonna explain it once more. Okay, so when we say soft labels of soft assignments, which are computed in this manner, what we're actually getting is, for example, let's say we have one data point, and the soft assignment for each data point and for each cluster could be, for example, 0.1, 0.7, 0.2. So it's a probability that the data point comes from cluster 1, 2, or 3. And the sum of these responsibilities should also be 1. Does it make sense? You can unmute yourself also if... Okay. And the shape of the Gaussians, I think, was here maybe. I guess that's related to this question. So here on the M step, we can see these kind of circles. They represent the density function in 2D. It's just a contour plot, which represents the where majority of data points would be for this distribution. And what I meant when I said the shape is changing, we can see that here the variance, the covariant matrix is diagonal, meaning that the Gaussian is spherical. And after update with the M step, we end up with the different covariant matrix and different mean vectors, which is represented by this changed shape of these circles, now ellipses. So that's basically what I meant with that. I hope it explains the question. Okay. Okay, we still have a time. So I wanted to show you a little bit maybe hands-on thing. How can you simulate federated learning experiments on clusters? So in your assignments, I assume you running your code on your local machine, probably on a few like processors. But if you want to scale up your experiments and probably you want to do more sophisticated federated learning experiments, you can also use different kind of approaches. And one of the interesting ways is to use the MPI or message passing interface. So MPI is the standard for creating communication between many tasks, or you can kind of say between the computing nodes or machines. And it used to run many programs in parallel. And it also allows to exchange of messages between different machines, different nodes. So this is a picture from the tutorial of Alta, Triton HPC. So here you have your machine, you log into our HPC cluster. where you have some nodes with the CPUs or GPUs. So, and essentially, instead of running your Python code just on your computer, what you can do, you can run your program on each node in parallel and also exchange the messages between the nodes. So this is very convenient for simulating federated learning experiments, because each node could represent the node of a graph. And then this message passing we can use for exchanging the model parameters. So with MPI, we can implement centralized federated learning or peer-to-peer federated learning. And because I mostly write in Python, so I also need to use a special library, for example, MPI for Python. And basically, in the terminology of MPI, each kind of a computing node or process is called rank. But in our federated learning terminology, rank would mean like a local node, like a local data set, local model. And we can use this message passing to exchange parameters and then construct the augmented data sets, right? So for ALT, if you want to try out on the Triton HPC, Alta provides implementation for this like MPA standard. It's called Open MPI, so you need to use this Open MPI and also additional library depending on what kind of language you use for the programming. Like, is it a C or is it a Python? And then you just use a normal like a Slurm task manager to run your script. So this MPI, Open MPI, is providing this MPI convolved object. You can imagine that this is a kind of a Python class object. And this object also provides certain methods. For example, you can broadcast messages to many nodes. You can send messages, you can receive messages, you can control the synchronization between the different parts of the code, and etc. So, and just to demonstrate how does it work, let's try it out. Let's see if I... Okay, so I'm already logged into Triton. And so what I have here, I have my Slurm script and I have my Python code. I'm not sure, is it visible? I don't think it's visible. Is it better? Okay. All right, let's see what we have in our script. So first of all, with the Triton, you can choose how many machines you're using. So for example, here I'm using 2 nodes or 2 machines. Then we can set up how many MPI processes we're using. In terms of federated learning, it means how many nodes of a graph we're using. So in this case, we have 12 nodes. And we also can set how many these tasks per machine we want to run, and some other metrics. Then we need to load necessary modules like Open MPI here. And then if you have environment, you need to activate the environment. And basically, that's all your script. It's pretty simple. And then in the Python file itself, what we have. So first we have to, as I said, use some additional library depending on your language. So in this case, it's MPI for Python. And after that, this is our main loop. where we initialize this communication object, which provides you with certain methods. And here, for example, get rank means get the ID of a certain client or like a rank. And each rank has a unique ID. And then we also can find out with the get size how many clients or ranks participating in this network. And then, okay, here for each rank or for each client, we have a local data set, which I just use scikit-learn make blobs function. It just generates a Gaussian mixture model. And we can also use our scikit-learn Gaussian mixture class and feed the local data. And then we're entering the training loop where we can send parameters to our neighbors. So for example, here for each neighbor in the list of neighbors, we are sending these initial parameters that we are learned. And then we also can receive the parameters from our neighbors. We need to be careful about like the order at which the messages are sent and received. So we need to make sure that all messages are the sending of the messages is complete and the receiving process also complete. And once we get once we exchange of the messages, then we can start with the constructing the augmented data set. Giving the neighbors parameters, we're just using again the scikit-learn GMM model and just sampling the data points from the neighboring distributions. And then we just refeed local model on this augmented data set. So that's basically it. Let's try to fetch, what was the name of them? Okay, we submitted job here, so it should take like 1 minute maybe to run. Then we can check the status. We can see that our process is running. And okay, let's wait a bit. So there is a question, is the MPI on Alta HPC Triton public? Yeah, I mean, everybody who has access to Triton can use it, yeah. Okay, let's see. Okay, we finished the work. Let's see what we have here. We can check also okay, we can check some statistics. So this is our job ID. We have our cluster Triton. This is my username. And for example, I use 2 nodes, cores per node, and then the statistics about the CPU utilized and efficiency, wall clock time, anything that you would need for like tracking your experiment. But the results are basically here. And let's see what our training return us. Okay, so so here we can see some print statements that I had in my Python file. And basically for each rank or each kind of a client, I asked to print out the host name and for the Slurm task manager, like a global ID, a local ID on which node it's running. So this is just some information that maybe you want to track while you're running your experiments. And we can see that we have like in total 12 clients, so 12 ranks, and each of them running this federated GMM separately on the CPU. So this is our adjacency kind of, it's not in the form of matrix, but this is a connectivity. For example, for the client 0, the neighbors are 1, 5, 6, 7, 11, and etc. So those are nodes between which the information is exchanged. And then we can print out different like statistics. For example, here I'm printing out for each client or for each node what the final means for each Gaussian the model learned, and I don't know, some other statistic. We have the centralized baseline here and some error statistic, like a difference between centralized solution and the local solution. So here we can see the results, and we can see, okay, the majority of nodes learned quite fine, but we have this kind of outlier here. So yeah. So this is basically it. So the only maybe another note is, yeah, you need to track how you're sending is, do you do synchronized, asynchronized, message passing, etc., to avoid deadlocks. And also I use only CPUs for this small simulation, like a demo, but you also can use GPUs if you have a larger model or data sets. Yeah, that's pretty much it. So if you have any questions about using Triton cluster for running federated learning experiments, you can also ask me, or any general questions.
Some discrepancy between the slides you're using and the slides on here. So will there be updates?
Yes. Yeah, I was just updating it before the like. Yes, I will update them. Okay, I don't see any questions, but yeah. Okay, thank you for participating. Then I think we're gonna finish here. Yeah. Keys. Yes, yeah, we'll upload the updated slides. Okay, bye-bye, everyone. Thanks.